Okay, so in this video lecture, we're going to continue our discussion of finding zeros of zeros of polynomial functions. And specifically, we're going to be looking at something called the rational zeros theorem, which has to do with finding zeros that happen to be rational numbers. So to start, to just sort of discuss what rational numbers are and to motivate the discussion a little bit to understand some of the abstractness that's going to be coming here in a few moments. If you took the linear binomial 2x minus 7 and the linear binomial 3x plus 5 and multiply them together, we get the quadratic trinomial 6x squared minus 11x minus 35. Now, if you think back to when you first learned how to solve quadratic equations like this, so if you had 6x squared minus 11x minus 35 equals 0, well, most likely you learned to use factoring before you ever learned about the quadratic formula. And if you factor 6x squared minus 11x minus 35 into these two factors that we have, 2x minus 7 and 3x plus 5, well, the only way that the product of two things is 0 is if one of those two things is itself 0. This is called the zero factor property, usually. And so if 2x minus 7 equals 0, for example, well, if 2x minus 7 equals 0, then 2x is equal to 7 divided by 2, and we get 7/2 as well as one solution of the equation 6x squared minus 11x minus 35. And in a similar way, you can get x equals negative 5/3 as the other solution. Now, if we think of the 6x squared minus 11x minus 35 as a function, I called it m of x here, well, the zeros of that are exactly what we just found, negative 5/3, positive 7/2. So remember what that means is that if you plug negative 5/3 in, m of negative 5/3 works out to be 0. You should check the arithmetic here. Excuse me. Okay, what I want you to note here is that if you take the denominator of this rational number, well, first of all, just to remind you, a rational number is any number that can be written as a ratio of two integers. So for example, negative 5 divided by 3, negative 5 is an integer, 3 is an integer. If you take negative 5 and divide it by 3, you get negative 5/3. You could also think of this as positive 5 divided by negative 3 as a ratio of integers. So a fraction, what we usually mean by fraction, is equivalent to a rational number. Now, every integer is a rational number. So 12, for example, could be written as 12 over 1 or 24 over 2. So rational numbers include the integers. Okay, so m of negative 5/3, as I mentioned, if you do the arithmetic, it turns out to be 0. But what I really want you to note here is that if you take the denominator of this rational number 3, it divides 6, which is the lead coefficient of our original polynomial. And if you take the numerator of the rational 0, 5, or negative 5, doesn't really make any difference, it divides the constant term of 35, or if you want to be more technical about it, it's actually negative 35, but again, doesn't really matter. 5 divides 35, negative 5 divides 35, 5 divides negative 35, so don't need to worry really about the negatives in looking at this. In a similar way, if we take the other 0, 7/2, the numerator divides the lead coefficient. Excuse me, the denominator divides the lead coefficient of 6, the numerator divides the constant term of 35. Now, this is what mathematicians call a necessary condition, meaning that if you have a rational 0, it has to satisfy the relationship that the denominator is going to divide the lead coefficient and the numerator is going to divide the constant. But although it's necessary, it's not sufficient. So just having it happen doesn't mean that you actually have a 0. So for example, 6 divides the lead coefficient, 35 divides the constant term, but if we went ahead and took 35 over 6, it's not a 0 of q. I was calling this thing q earlier. It should be m. when I originally wrote it up, I called it Q, changed my mind on what I wanted to call it, and forgot to change that. Okay. So the point is that just because you can create a rational zero by looking at the lead coefficient and the constant term, doesn't mean that that zero will actually be, that rational number will be a zero of the original polynomial. But if there is a rational zero, you'll find it by this process. So the rational zeros theorem is this here. If you have a polynomial, f of x equals a sub n x to the nth plus a sub n minus 1 x to the n minus 1 plus dot 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 all the way down to the last few terms, which could be a sub 1 x plus a sub 0. We have a polynomial function that's just a generic representation of a polynomial function. The coefficients have to be integers. So the a sub n minus 1, so on are all integers. That's typically what you see in math classes anyway. If they are rational numbers, it'd be possible to change the rational coefficients so that they become integer coefficients. And typically we don't see non-real complex numbers as coefficients. We don't even usually see things like the square root of 3, but you could have a square root of 3. It would be a polynomial if we had a square root of 3 times x squared. It's a polynomial function or a polynomial expression. But that wouldn't fit into this category, this particular, of the rational zeros theorem. If you have a rational zero of that, it can be written in the form p over q. Should be noted that p over q, we're assuming, has been reduced to lowest terms. So if p and q have any factors in common, those are canceled out. So you wouldn't have 2 over 4. That would be reduced to 1 over 2. Anyway, we can find all possible rational zeros by looking at the p and recognizing that it has to be a factor of the constant at the end. And the q has to be a factor of the lead coefficient of a sub n. So look for an example of this. Here I have a function I'm calling f of x, 9x cubed minus 16x squared minus 13x minus 2. The possible choices for p would be plus or minus 1 or plus or minus 2. So the p, which is the numerator of our polynomial, so p over q, alphabetical, p in the numerator, q in the denominator. The p goes with the last thing, the q goes with the first thing. With practice, that's something you'll remember. I forget it all the time because I don't practice it very often. So anyway, if you look at -2, don't really need to worry about the negatives. We're going to have plus or minus, and really don't need to have all these plus or minuses. Just in the end, it's going to be a positive or a negative. We need to consider both cases. So anyway, the factors of 2 are 1 and 2. And for completeness, I wrote plus or minus 1, plus or minus 2. If you look at 9, its only factors are 1. 1, of course, is always the factor of everything. 3 and 9. So we don't have too many choices there. We have 2 choices here. We have 3 choices there. So that would be a grand total of 6 different possibilities, just based on that. Though sometimes you'll have replication of things and looking at that. So one possibility, for example, is you could take the 2 and divide it by the 1. So 2 is a possibility. -2 would also be a possibility. Well, you can check and see whether 2 works by just plugging it into the original. Work it out. F of 2 is -20, not 0. So 2 is not a 0. If you were to play around with it, you might eventually come across the idea of taking the 2 and dividing it by the 3 or the 9. And it might be positive, it might be negative. Well, if I calculate f of -2/9, so I'll put that in for x, you cube it. Cube of the negative is negative, so 2 cubed is 8, 9 cubed 729. You cube square -2/9, so you get 4 over 81, which is positive because negative times negative is positive. And so I did some of basically just the cubing and the squaring on this line here. You then multiply it out. Well, since 9 and 7 goes into 729, you can actually cancel out the 9 and the 729 to get 81. So you get negative 8 over 81 for the first term. Second term, 16 times 4 is 64. So you get negative 64 over 81. And then this term here, we've got negative 13 times negative 2 ninths. The negative and negative make positive, 26 ninths. And then we end up a negative 2 at the end. Get a common denominator of 81. And if you add these terms together, they do add up to 0. So negative 2 ninths is a 0 of our polynomial. Now, according to something called the factor theorem, if we have a 0, let's call it z for 0. If z is a 0, then it follows that x minus z is a factor. Factor means that I can divide the original polynomial by x minus z, and by doing that, I'll reduce the degree of the polynomial. So specifically, negative 2 ninths was a 0 of f, so x minus negative 2 ninths, that's x plus 2 ninths, is a factor of f of x. 9x cubed minus 16x squared minus 13x minus 2, if you've forgotten. You can divide this out with long division. That's what I do most of the time. Hardly ever use synthetic division, but I decided to do it once here just for fun. It's a good idea every couple of years to bring out some of this algebra that maybe don't use on a regular basis and just try to remember how it works. So the idea is, instead of writing out the entire thing, we just write down the coefficients: 9, negative 16, negative 13, negative 2. It has to be in order. Over here, out here in front, I wrote down negative 2 ninths. So if we have x minus something, we can divide using synthetic division. It's x minus negative 2 ninths. That's why I wrote minus 2 ninths out here. And the way synthetic division works is you take the lead coefficient here and you just bring it down to the bottom. We multiply that by the number out here that we're sort of dividing by. We have negative 2 ninths times 9. That gives me negative 2, which you wrote here. We add these two numbers together. So synthetic division is designed in a way where we can avoid really the divisions replaced by multiplication and the subtractions replaced by addition. So negative 16 and negative 2 added to negative 18. Repeat the process. Negative 2 ninths times negative 18. Well, negative times negative is positive. The 9 goes into 18 2 times. 2 times 2 is 4. So negative 2 ninths times negative 18 is 4. Again, we add that to negative 13 to get negative 9. Do it again. Negative 2 ninths times negative 9. And get 2, which adds to the negative 2, we get a 0. The remainder has to be 0 because that's really what tells us that this is the x minus negative 2 ninths, the x plus 2 ninths is a factor. It also ties into something called the remainder theorem, which is not in my estimation in mathematics anymore, since we have calculators nowadays. But the remainder theorem says that if you plug negative 2 ninths into the polynomial, which we did up here, what you'll get is the remainder if you divide by x plus 2 ninths or x minus negative 2 ninths. And so you can actually use synthetic division then to evaluate a polynomial. Back in the days when we didn't have calculators, that was actually an easier way of evaluating polynomials. But with the advent of calculators, computers, and all that stuff, the remainder theorem is not something that has a whole lot of practical value. Everything in mathematics has its own little inherent value and sometimes some theoretical value, even if there's no practical value. Anyway, back to the long division. This thing at the bottom here, the last thing here is the remainder. That's sometimes actually set off by a little box here. The 9, negative 18, and negative 9, those are actually the coefficients of what you get if you divide this. So when you divide it by x plus 2 ninths, you're going to reduce the degree of everything by 1. And we get 3 terms, 9x squared minus 18x minus 9. So I wrote that out here. F of x equals, there's the original polynomial 9x cubed minus 16x squared minus 13x minus 2, I rewrote it as x plus 2/9 times the 9x squared minus 18. Oops, that's not right. Better fix that. Or else it showed up, it's also wrong. Let's see if it's right now. Okay. No, one last correction. Boy, it's always a good idea to look at your math at least a couple of times. And normally a good idea to leave it alone for a while and come back to it with a pair of fresh eyes. Because unless you're just not like me, one of those people, maybe you're one of those people who never makes mistakes. And I make them, unfortunately, all the time. Okay, so anyway, the 9x squared minus 18x minus 9 that you see here, I got that from these three numbers, 9x squared minus 18x minus 9. And knowing what the power is here, that this is x squared, this is x, this is constant, that's a matter of knowing that I reduced the degree by 1 when I do this. So this was third degree, it has to go down to second degree, so this has to be second degree. One after that would be first degree, one after that would be 0 degree or constant. Last thing, again, is the remainder. You can ignore synthetic division if you want to, as long as you can do regular division. And regular division is actually more general than synthetic division, so you need to be able to do the regular division even if you can do the synthetic division. But synthetic division does save a little bit of effort sometimes. Okay, so anyway, I factored it using what I discovered here in the factor theorem and all that. And just decided to do a little bit of manipulation to write it in a slightly different format. Factored out the 9 from the 9x squared minus 18x minus 9. And then if I take that 9, I could just leave it floating out there, but I decided to get rid of the fraction 2/9 by multiplying the 9 times the x plus 2/9, which gives me 9x plus 2. You should check when you get a chance by multiplying this out. Pause the video, multiply it out, see that it does give us the original third degree polynomial. You can use the quadratic formula to find the zeros of there's that error again. What happens with cutting and pasting, you're copying and pasting your errors. Okay. So anyway, if you use the quadratic formula to solve the equation 2x squared minus 2x minus 1 equals 0. So I take the parentheses out. They don't hurt anything, but I don't really need them. The solutions to the equation x squared minus 2x minus 1 equals 0, or the zeros of the function y equals x squared minus 2x minus 1. Those zeros are x equals 1 plus the radical 2 and 1 minus radical 2. 1 plus or minus root 2 are the two solutions to this equation. So what we know here about our polynomial, 9x cubed minus 16x squared minus 13x minus 2, well, if I look at the degree, it's third degree. The lead coefficient is positive. And so based on that, I know the right tail is going to go up, the left tail is going to go down. It's going to have a y-intercept of -2, which we can figure out from this thing right here. If you plug in f of 0, you get -2. And the x-intercepts are -2/9, which we worked out earlier, and 1 plus square root of 2, 1 minus square root of 2. So if I wanted to, let's go ahead and look at a different screen share here, the whiteboard. So if I wanted to go ahead and do a real quick sketch of that. Yes. Oh, what's a good color for a? I'll try that color. Okay. So we have, negative 2/9 was the first zero we started with, so that's about negative 0.2. We also have 1 minus the square root of 2, which is about negative 0.4. So those two zeros, so negative 0.2 and negative 0.4 would be about there and there, real roughly, which means that negative 1 would be about here. Just put that there for reference. Negative 2 was the y-intercept. So let's say that's negative 2 there. And then the other zero we had was at about 2.4, 1 plus the square root of 2. So 2.4 on this scale would be, let's say, really roughly about there. So there's 1, 2, yeah, 2.4 would be somewhere around there. Now we have 3 zeros. If we were to write this in factored form, the f of x, the factors would be the x plus 2/9 that we saw, and we'd have x minus the one irrational number and x minus the other irrational number. In other words, we'd have 3 factors. Each would have a multiplicity of 1, so it's going to cross at each of these zeros. If you think about it, you should be able to convince yourself that it has to cross for this to work out. So off to this side, it's going to do something like that. So this zero was at 1 plus radical 2, which again is about 2.4. And then we have the other zeros here, and it's going to have to come up and cross, come back down. I don't really know anything about how high it goes, so I just writing a little graph here, recognizing that there are things about the graph that are not necessarily correct. So this one here, so the negative 2/9 was the one back. If I try writing them, they're just going to make a mess. So 1 minus square root of 2 is this 0, and negative 2/9 is that 0. So it crosses at those 3 places. We know that this thing can have as many as 2 turning points. It clearly does have 2 turning points. Y-intercept is negative 2, but it could go down from that. I really shouldn't have tried to imply that it's that. So again, this sketch is not accurate by any means. It's a rough sketch. It's a first draft of what we're looking with that. Thank you for watching.